All right, so our last speaker for this session in the afternoon is Suyash Kumar, who is joining us for his second summer at CASSI. He's joined us again from UCLA, where he'll be a senior this coming fall. This summer, he's been working with Lauren Anderson, and he'll tell us today about their project, Data-Driven Interstellar Dust, constructing a 3D dust map of the Milky Way. Go ahead whenever you're ready.
Thank you so much for the introduction, Gwen. I'm very glad to have all of you at the symposium today, and I'm excited to tell you more about my research. So to kick things off, what even is a dust map? So a dust map is shorthand for dust density as a function of position, and it's usually defined everywhere in space and changes smoothly. And because it's defined everywhere in 3D space, it can be a bit difficult to visualize it in 3 dimensions. So a common technique is to take slices along one of the dimensions. And that's why you only see x1 and x2 up here, because this is a slice along the x3 dimension. And this is an example dust map and a template for how we'll be visualizing dust maps in this talk. But another important question is, why should we even care about dust? To answer that, I have a motivating example. On the left-hand side, we have the model spectrum of a star that's unobscured by dust. And on the right-hand side, we have its position on the color magnitude diagram. Now, depending on the amount of dust that's between us and the star, the observed spectrum and the position of the star on the color magnitude diagram can shift. And unless we can actually correct for these errors, we can end up misinterpreting our observations. And that is exactly where a dust map can help us correct these errors. Now, our wishes are complicated by the fact that we cannot directly observe the dust density at isolated points in space. What we can observe are where stars are and the total amounts of dust between us and stars along lines of sight. These quantities are called extinctions and are essentially integrals of the dust field that we must undo in order to find out the dust density at all points in space. Daunting as that may seem, we actually have a model that is capable of achieving that, and it is called hierarchical inducing Pointgaussian process, and it is a probabilistic regression model that can scale to large amounts of data. The way it works in particular for our case is that the model looks at a field of stars with their extinctions and positions given to it, and it tries to learn the underlying density, finally giving us a predicted dust map. But the most important question is, how is it that the model learns the underlying density? Well, to answer that, let's think of an intuitive case where we can imagine two stars being along the same line of sight, and we also have access to their respective extinctions. Now, in an ideal case, if space is infinitely filled up with stars, we can choose two stars such that they are very close together. And because we already assume that the dust density changes smoothly and slowly, we can assume it to be roughly constant over this small segment between the two stars. And therefore, when we subtract off the extinctions from each other, it would be equal to the density in the small region times the length of that region. And from there, we can work out the density. Now, that's all good, but the issue is that we don't have an infinite number of stars. Like in the schematic right here, if you look at the pink region, we don't have any stars there. So we can't use the method I told you a slide ago to calculate the densities. But not all hope is lost. We can still do the following trick. So we must assign the density function to be a joint normal distribution across various points. What does that mean? Imagine taking 2 points in this pink region, for example. Now, their respective density values would be governed by a joint probability distribution, which basically says that certain combinations of density in these 2 points are more likely than other combinations. But physically, we would like the most likely combination to best explain the extinctions of stars that are in our region of interest. And so the general workflow of the model is that you take initial guesses for some of the model parameters, which are commonly called hyperparameters. And some examples can be the width of this Gaussian or the height of this Gaussian. And using these initial guesses, we can basically get a test density function from which we can generate extinctions of all the stars in our region of interest and comparing them to the true extinctions that our model has access to. The hyperparameters can be tuned to better explain the stellar extinctions. Now, some of that tuning comes automatically with the model using methods like gradient descent, but some of the parameters cannot be tuned that way, and we would simply have to take a new initial guess and repeat this process. And to top that off, the model's performance can be highly sensitive to these initial guesses. So this can be very much a feedback process and it can take a lot of time. But ideally, our model should be able to look at the extinctions and figure out the underlying dust map, which is definitely quite ambitious. So we should ask, what is it that we can achieve? Now, we'll first validate our model over simulation because in a simulation, we actually have access to the true dust map. For example, here I have the dust map from a Milky Way-like simulation from the latte suit. But remember that the model cannot actually look at this. What it can look at are stellar extinctions, and I present a 2D slice of them up here. And looking at these, our model comes up with a predicted dust map and variances, which you can take the square root of to find out the errors. Now, the beautiful thing is that the model never actually had a chance to look at this dust map and still came up with this answer that is eerily close, which is a great thing because we know that our model can perform well. But nonetheless, that's over a simulation. We actually want a dust map of the Milky Way. Can our model do that for us? Let's check it out. Well, in the Milky Way, one slight complication is that we don't actually have a true dust map to compare our answers to, because that's what we are trying to predict in the first place. But nonetheless, we have extinctions like before, but not from simulations, but from Gaia and Apogee stellar surveys. And using these extinctions, our model can come up with a dust map and associated variances. As you can see, the scale of these variances is pretty high compared to the predicted means, which basically implies that our model is a bit shaky in its prediction, which can also be confirmed from the astrophysics of this dust map, because this big blob that you see right here is actually located in a region that belongs to the local spiral arm. So we shouldn't really have a huge dust blob there, or we wouldn't really be having this presentation. But anyways, if you look around that central dust blob, we have a bunch of dust clouds that look kind of feasible. So it seems that our model is getting a few things correct and a few things not so much. So maybe we can try zooming out in spatial extent so that our model is not burdened with resolving these particular tiny features. And again, to do that, we should validate over a simulation again to form a baseline expectation. Now, this is the same dust map as before, but zoomed out, and the model cannot simply look at this. What we give the model are stellar extinctions like before, and our model comes up with a prediction and associated variances, which are definitely higher compared to the variances we saw in the small scale simulation dust map. And that is not too surprising because it seems that the predicted densities have a hard time capturing all the dust features here. The good thing, however, is that the predicted densities are at least in the same order of magnitude. So from this exercise, what we can infer is that it can take quite a bit of effort to get a good quality dust map for a large spatial extent, but we'll still go ahead and give it a whirl for our Milky Way data. So once again, we do not have a true dust map to compare our answer to, but we go ahead and give our model stellar extinctions from Gaia and Apogee, and our model comes up again with a predicted dust map and associated variances, which again are really large. And you may recall that from having looked at our small scale Milky Way dust map. Now, if you give this a good hard stare, you may realize that this dust map kind of looks like an extension of the small scale Milky Way dust map that we created before. So this blob definitely persists from before. And you can look at these clouds around the blob, which kind of look feasible and look like an extension of the dust clouds that we saw in the small scale Milky Way. So that said, we have covered a lot of dust maps, so it's a good idea to make a grid of our results to kind of wrap our head around this journey that we took. So we started out with a small scale simulation, roughly around zero point 0.5 kiloparsecs on the side, where we were able to get a predicted dust map that we were really happy with because it captured all the features. And from there, we were confident and went on to create a Milky Way dust map across the same scale using Gaia data. And this time, we got the central blob at the center, but apart from that, we still have some feasible dust clouds around it, which gives us some hope. So to curtail the model from having to focus on very specific features, we kind of zoom out and try to create a dust map for 1 kiloparsec scale this time. And the model, while not having to deal with very tiny features, has to deal with a lot of features, so ends up assigning too many dust clouds. And finally, we created a Milky Way dust map across the large scale, which kind of looks like an extension of the small scale dust map and has feasible clouds around the central blob that our model is having a tough time resolving. And by the way, for our simulation dust map, we did get magnitude dust means in the right order of magnitude. So in summary, HipGP is a method that can use extinctions and stellar positions and give us a dust map. And in this project, we validate it on a small scale latte simulation and try to extend the domain of this model to observational data and large spatial extent. In terms of conclusion, we were really happy with our model's performance over the small scale latte simulation, but in terms of observational data or larger spatial extent, there still needs to be more work done. And the first thing that we would want to do is develop more intuition about how our model reacts to various initial guesses for hyperparameters. And we would also like to train our model for longer, and having access to GPUs with greater memory capacity would be a great plus. But that's all I have for this talk, and I'm happy to answer any questions. Thank you.
All right, very nice, Suyash. Do we have questions for Suyash about this presentation? So I was curious, for the actual data set they're using, the combination of Gaia and Apogee, I imagine this is a very small and sort of local subsample of the data that are across those two surveys. But do you have any information about like the plausibility of extending this to even still larger scales, and if there's anything to be learned by doing that, or if the goal is mostly to have a map that is somewhat more local?
That's a wonderful question. Thank you for that. So one of the most scary things is that the model takes distances as a certain right now. And as we go farther out in scale, distances naturally become uncertain. And so what the model can end up doing is that it can end up attributing some of the uncertainties that come from other variables into more dust. And that is actually also one of the reasons why we sort of suspect that big blob we saw at the center. So that is definitely one thing that we would need to be cautious about, to include more uncertainties for other quantities. And another thing that would definitely need to be tackled would be the computational cost of extending the spatial scale. It's not exactly the number of stars that just cause the issue, it's also the amount of dust features that you need to resolve that can become an increasingly difficult problem. So to get like a dust map of a reasonable resolution on a larger scale would definitely have to have some more optimizations being put into this model.
Perfect. All right. Do we have any other questions for Suyash? Ova?
Yes. Hi, Suyash. Thank you so much. It was very nice to see. And it was cool to see that you zoom out a little bit. And I wanted to ask whether you have any idea of why the model couldn't do as well when you zoom out in your fake data compared to the smaller scale, because it's not that much difference. And I guess that I'm not completely following why that was difficult.
Yeah, that's a wonderful question. I'll bring up that slide. Yeah. So a couple of things here. So compared to the small scale model, you can see that there are like a lot more features to capture this time around. So that those two small blobs that you see were the only features in the dust map before, but now you sort of have like these features popping around at the corners. And I mean, the corners kind of definitely pose a problem because the model tends to falter around the corners a bit. So probably that could confuse the model somewhat. And well, also, it's just that we have simply more dust features to resolve. So getting up to like a reasonable resolution imposes additional cost, and optimization just becomes more difficult. But we are actually currently conducting what is called a grid test to understand sort of how the model is coming up with different guesses based on some of the hyperparameters. And you can see that the model's behavior is fairly chaotic. Like these are just two of the many hyperparameters, and we vary both of them across like 3 orders of magnitude. And the model comes up with pretty different initial guesses in terms of structure, and also like the means, if you can see them, like they vary across orders of magnitude. So it is a problem that we are trying to tackle right now. But I hope that answers some part of it.
Yeah, thank you. Very interesting. So
Yeah.
maybe if you would not have borders, like if it struggles at the corners, does it help? Like if you would remove the edges?
Yeah, so yeah, that's a great question. So we should probably have tried focusing on maybe a slightly smaller, like an intermediate scale where those corner features are not there, to see if the model still gets confused. That's a great idea. I will actually try that out.
Interesting. Well, very nice to see you. Yes.
Thank you.
Okay, I think we have time for one more question. Alex, did you have a question?
Yeah. Question about the you mentioned that you need a GPU with bigger memory. So I was just wondering what does that mean, and how big would you want it other than as big as possible?
Yeah, that's a wonderful question. I am actually not super familiar about like the exact memory quantities, but I can answer that question kind of based on time. So some of the like best trained maps that we saw, for example, the small scale dust map right here, this sort of trained for like 20 hours or something. And like it, and apart from that, like for if you want to get sort of a reasonable estimate, it can take anywhere between half an hour to 1 hour to like train over your training data set for one epoch. So it's just that like if that time could kind of be reduced by using a better GPU, we could perform grid tests like this much faster and get a better idea of like how exactly it is that our model reacts to the hyperparameter initial guesses. So I would guess even half an order, like half the time would help somewhat. So yeah, that's kind of my estimate. Sorry, it wasn't really specific in terms of like memory or.
No, that was really helpful. Thank you.
Yeah, sure.
All right, perfect. Let's thank Suyash again for his presentation.